Hello, lovely students. Today we're going to be talking about the fundamental theorem of calculus, and you've actually learned a piece of this theorem, right? This theorem is what allows us to evaluate an integral, right? It tells us that the value of an integral is the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. So that's one piece of the fundamental theorem of calculus. What we're going to do today deals with the other piece of that. So what we're going to look at today is problems that look like this. So asking us to take the derivative of an integral, and we're going to see what happens when we do that. So before we really dive into what the theorem tells us, we're going to try out this problem. So when I'm tackling this, I'm going to deal with the integral piece first, and then I'll deal with the derivative. So for right now, I'll copy that derivative notation, but we're not going to do anything with it yet. So I know, again, by that first fundamental theorem, that to evaluate this integral, I need to find the antiderivative. Well, the antiderivative of cosine of t dt is just going to be sine of t plus c, and I'm going to evaluate that from 3x to x squared. Now this looks a little different because my upper and lower bounds aren't numbers in this case, but we're going to handle it the same way. So again, I'm going to leave this derivative out here. We'll deal with that in a little bit. So now I can take my function and evaluate it at the upper bound. So I have sine of x squared plus c, and I'm going to subtract that antiderivative evaluated at the lower bound. So minus sine of 3x plus c. So if I simplify that a bit, we know that our c's are going to cancel. When I distribute that negative, that becomes a minus c. So that's going to go away. I should have had actually another set of parentheses. Well, you get the idea. There we go. So when I distribute that negative, the c's are going to cancel. So what I'm left with for my function is sine of x squared minus the sine of 3x. So I've dealt with just the integral part here. That's what we accomplished so far. And now we're going to go ahead and differentiate with respect to x. So for my first term, I know this derivative of sine is cosine of x squared. But now, because of this piece here, I need to use the chain rule. So I'm going to multiply that by 2x. Now my second term, again, my derivative is cosine of 3x, but chain rule says I have to take the derivative of that, and so I'm going to multiply by 3. So I end up with 2x times the cosine of x squared minus 3 times the cosine of x. Now, here's where I want us to kind of make a few connections before we move on and generalize this rule. So I started off with the derivative of an integral. And here's what I got when I simplified this problem. Here's what I want us to see. When I took the derivative of that integral, I ended up with that same cosine function that was in my original. Right, so my first term here, I have the cosine evaluated at that upper bound, right? My x squared here became the argument of cosine. And then in my second term, oops, if I had written this correctly, it should say 3 times the cosine of 3x. Sorry about that. You probably caught that before I did. Right, now this lower bound is my argument of cosine here. And then the only other piece is here I have the derivative of my upper bound, and here, this is the derivative of the lower bound. So I'm going to make a couple notes here. Right? My 2x here I know is the derivative of the upper bound, and the 3 is the derivative of the lower bound. So what I'm noticing is that taking the derivative of the integral, those basically just kind of wiped each other out. Those are inverse processes. So I ended up with the same function here as I did in my answer here. Now, we're going to have a rule here. Instead of having to go through this process each time, the fundamental theorem allows us to kind of distill this into a rule that we can apply every time. So So the big idea is, can we create a rule that will allow us to take the derivative of an integral more efficiently? And obviously the answer is yes, we can. So here's what happens. We said when we took the derivative of the integral, we ended up with the same function. Sorry, I'm pointing and you can't see. Same function that was in our integral. So in this case, we would have f of something, and then we subtracted, right? And we had that same function, f of something. Now, in my first term here, so my function came from here. My first term, I'm going to plug in b, right? Just like up here, we plugged in our x squared. But now I have to multiply, and I should have left more room. I have to multiply by the derivative of b with respect to x. So I have f of b times db dx minus, now I'm going to deal with that lower bound, f of a times dA dx. And that rule will work every time. So if we're trying to find the derivative of the integral, this is the process we're going to follow. So let's go ahead and do a couple of these. We won't do all of them that are in the notes, but we'll do a few here. And then if we need to practice more when we're back together in class, we can do that. So here's what a problem is going to look like. Now we're going to have functions that are defined as integrals, and we're going to be asked to define the derivative of those functions. So for this problem, I'm trying to find dy dx, the derivative of y with respect to x. So I know that's going to be the derivative with respect to x of this integral here. So in this first step, all I did was introduce that derivative notation. Now I'm going to go ahead and apply what we said on the previous page. So I know if I'm taking the derivative of this integral, I'm going to have my same function. So it's going to be the sine function. Then we said we're going to evaluate that at the upper limit. So instead of t, I'm replacing that with x. So I have sine of x, and in this case that happened to be squared. And then I'm going to multiply by the derivative of x, which is just 1 in this case. Now again, I have the same function, that sine function. My lower bound is 4, so instead of t, I'm going to replace that with a 4 squared. And now that derivative is 0. So actually what's going to happen here is we're only going to have one term in our answer, because this, if I multiply by 0, this term is going to drop out. So what I get is that my derivative of y with respect to x is just going to be sine of x squared. Again, important things to notice here. That sine that was in my integral was the same function that's in my derivative. My x came from the upper bound, and I squared it because this was t squared. And the 4 down here comes from the lower bound. All right, let's try the next one. Now, this is only slightly more complicated, because now instead of x, I have a function in terms of x. I'm going to have to be a little careful there not to forget my chain rule. So again, the derivative of y with respect to x is just going to be the derivative of this integral. Okay, so again, we know my function here is a sine. So I'm going to have a sine function in both of my terms. So maybe I'll leave some space here and sine. That sine function is not going to change. Now, for my first argument, instead of a t, I'm going to plug in my upper bound. So I get 3x squared plus 7x. Since this was a t squared, I still need to square that. Then I need to multiply by the derivative of that upper bound. So I'm going to multiply by, let's see, 6x plus 7. Now, for my second term, I'm replacing t with my lower bound, which is just a 4. I'm going to multiply by the derivative of my lower bound, which is 0. So what we see again is that our second term is dropping out. Hopefully what you're noticing is whenever you have a constant as one of your limits of integration, that term is going to drop out when we multiply by the derivative of that constant. So now my derivative is, I'm just going to rearrange it a bit, 6x plus 7 times the sine of 3x squared plus 7x quantity squared. All right, for the next one, again, same idea here. And actually, let's see. Well, we'll go ahead and do this one, even though it's the same function. So we're going to take the derivative. It's the derivative with respect to x of our integral. Okay, so now, this one's interesting because I notice now my constant limit of integration is on top instead of on bottom. So let's see what effect that has. So we're going to proceed the same. I'm still dealing with sine. Instead of t, I'm going to plug in my 7. And then I'm going to multiply by that upper bound. I'm going to subtract. Now I have sine. Instead of t, I'm replacing it with 3x plus 2. And I'm going to square that. And then I'm going to multiply by the derivative of 3x plus 2, which is 3. So now I see that term in front is the one that's 0. So I end up with the opposite of 3 times the sine of 3x plus 2 quantity squared. Now I want to think for a little bit about why it makes sense that this would be a negative here when all my others have been positive. But if we think about properties of integrals, I know that if I switch the bounds, I make this an opposite. So in other words, if I were to put 7 on the bottom and 3x plus 2 on top, changing the order of integration changes the signs. So it makes sense now that since my 7 was on top, that's the same as taking the opposite of the answer I would get if that 7 were on the bottom. So that's why my first two answers were positive, and here I'm getting a negative. All right, we're just going to do one more, and then we'll move on for today. So here, let's see. You know what? Actually, I'm going to skip 4. I'm going to go down to 5 really quick. This one's a little different. Now I don't have any bound that's a constant. They're both functions in terms of x. So let's see how this looks. So derivative of y with respect to x is the derivative with respect to x of my integral. Okay. Same process applies here. I have my function 2 plus e to the t. So I'm going to start with that, 1 over 2 plus e to the, now I'm going to evaluate at my upper bound. So it's e to the x squared, and I multiply by the derivative of the upper bound, which is 2x. Now I'm going to subtract. I have my same function, 2 plus e. In this case, my lower bound, I'm going to replace t with the 2x, and I'm going to multiply by 2, which is the derivative of that bound. So now I have 2x over, let's see, 2 plus e to the x squared minus 2 over 2 plus e to the 2x. So you can see in this term, or excuse me, this problem, since both bounds were functions in terms of x, I'm going to have 2 terms in my derivative. And we're going to be really careful here. We're not canceling any 2's because on the bottom, both terms don't have a factor of 2, so I can't cancel out those 2's.